Hi, welcome back. We're in the third segment of lecture 15, and now we'll do a one-way ANOVA in R using the same example, the working memory training experiment. Remember, the authors approached their data a couple different ways. So here, we're just going to zoom in on the folks who are in one of the various training conditions. So we're just going to use number of sessions as the independent variable, and then for simplicity, we're just going to use the gain score as the dependent variable. Again, it's this result that we're going to analyze. So these represent 4 different groups, and on the y-axis are their gain scores, post minus pre. Since we have 4 different groups, it's best to do a one-way between groups ANOVA. We don't want to do multiple pairwise t-tests, 1, because it's tedious, and 2, because it increases the probability of type 1 error. Right? Every time we keep doing another NHST, we risk committing a type 1 error. So it's more appropriate to do the one way between groups ANOVA and follow it up with post hoc tests, which we'll do here in the script. So here's the R code for the ANOVA. I didn't repeat all the introductory code. You have it from the last segment. So assume that you have the data in there. We did the subsetting. So we're just going to look at the training folks. So again, the essential function here is AOV to call the ANOVA function. And it's just AOV open paren dv tilde iv. So my dv is gain, my iv is condition. Note this data frame's a little tricky, right? Because I've used training as an independent variable, but that was just whether people were in training or not. So that was just coded as 1 and 0. 1 for people who are training, 0, no training. There's another variable called con for condition. That is how many training sessions were they in. And if you peek at the data frame, that should be clear. Then I can do the summary function that will give me the summary table for this ANOVA call. And I did this sort of extra step here, again, because we want to calculate effect size. So we need to save the summary table or summary output into a table so that we can access it to get sums of squares, because remember, to calculate effect size, we need to calculate eta squared, so we need sums of squares. So we need to save that summary table and then index it so we can do a calculation. As I said, we actually have a function, because we do this all the time. We have a function that does this. And at the end, I'll show you that. Then we want to do post hoc tests. There are several procedures available to you. I tend to rely on Tukey's HSD. It's Tukey's honestly significant difference. John Tukey was a professor at Princeton. It's a very simple, straightforward approach, so I like it. Again, the point of the post hoc tests, and the reason why there are so many of them, is they all correct for this increase in the probability of type 1 error as you start doing multiple comparisons. And statisticians argue about the extent to which you want to control or threshold that increase in probability of type 1 error. So there are several different procedures. To me, Tukey's is one of the most intuitive and straightforward, so I tend to rely on that. But you can go explore in R. There are lots of other ones. They're not going to make a big difference, by the way. Then we don't forget this homogeneity of variance assumption in one-way ANOVA. We assume that the amount of within groups variance in each condition is approximately equal. And the way to test that is by doing a Levene's test. And oddly enough, that's not in the psych package. We need to develop our own package for this course. So I just found it in the car package. So again, you're going to have to go do install.packages, open paren, open paren, open quotes, car, close quotes, close paren, and choose your CRAN, and download the car package, use library car to load it. There's the function Levene tests, and it's just the dv, the iv, and I use this argument center equals mean because it turns out that the default in R for the Levene test, at least in the CAR package, is it uses the median in a condition in the Levene test, which you could make an argument for that. You could make an argument for the mean. Sort of splitting hairs there, but I'm used to doing it with the mean. That's the default in SPSS, which is the software I used to use. So I flipped that argument on, center equals mean. If you don't put it in there, then it's going to use the median. Okay, here's the output. So at the top, this should look familiar. It's just an ANOVA summary table. And it's just a one-way between groups ANOVA. And there were 4 levels of the independent variable, that condition. So degrees of freedom is 3. And the residuals, or the error term, what I was using in my notation was S within A, right? So subjects within groups. Why are subjects within groups differing from one another? Why is there variance? We don't know. That's just residual error variance. So R calls it residuals. And they see this, it's always the same structure. Degrees of freedom, sums of squares. Then the mean squares is sums of squares over degrees of freedom. F is mean squares between over mean squares within. Get a really big F value here again. I think it's because I didn't throw in enough within groups variance. But again, it mimics the results of Yaki et al. We have a significant effect of training sessions. To get the effect size, here's the code again. And the effect size in ANOVA is eta squared. That's the proportion of variance in the dependent variable accounted for by the independent variable. And in this case, again, it's pretty large, 58%. So looks like a pretty powerful training effect. But we don't know at this point, do the different training conditions differ from one another? All we know is overall there's an effect somewhere. So if we just looked at this, it might be possible that there's just a difference between the 2 extreme groups, so 8 and 19, right? We have to do the Tukey's post hoc to see. So here's the output for the Tukey's post hoc test. What Tukey's does, as I said, it's pretty intuitive and straightforward. It just does every pairwise comparison, and it adjusts the p-values accordingly. So according to how many pairwise comparisons there are. So you see they're all listed out here. These are the different scores for each pairwise comparison. So the first one is 12 versus 8. And the difference between 12 versus 8 was just 1.25. But it's actually, and see this is an adjusted p-value. That's where the ADJ comes from, is adjusted p-value. Again, adjusted to control that inflation of type 1 error. So just to be clear on that, if you just did a t-test comparing the 12 session group to the 8 session group, if you just did a t-test, you'd get a lower p-value because there wouldn't be any sort of adjustment if it was just done by itself. But what you're seeing here, if you look at this last column, is if we use 0.05 as the cutoff, all the pairwise comparisons are significant. So as we go up in that graph in Yaki et al., what that's saying is for each step is a significant jump in gain score. Finally, and sort of being a poor teacher here, I should have done this at the outset. Test the assumptions first, right? But I didn't want to get bogged down in it. And I just want to illustrate that we didn't violate the homogeneity of variance assumption, but you should really do this at the outset. Again, the way to do that is to call the Levene function. And what you see is you get an F value because it's doing a one-way ANOVA. It's just doing a one-way ANOVA. Instead of comparing the group means, it's comparing the group variances. So it just calculates the variances. And that's why I put center equals mean, because I'm used to calculating variance. Remember, go back to descriptive statistics. By getting deviation scores, taking each individual score and comparing it to the mean. So that's how this Levene test will work if we set center equals mean. If we don't, R's default, interestingly, is center equals median. So it would calculate variance according to the median. So the deviation scores would be each individual score minus the median for that group. So it's a little different. In any case, what we see here is an F value right around 1, right? That's what we would expect just due to chance. So good. That means we did not violate the homogeneity variance assumption. I knew that because I made up the data. So the p-value is 0.34, nowhere near 0.05. So we're safe. Again, let's interpret that. What this means is this overall effect is significant. We got that from the first F ratio and the big eta squared. And then by looking at the Tukey's tests, what we see is each pairwise comparison, so from here to here, and then from 12 to 17, and from 17 to 19, every pairwise comparison, they're significantly different. Okay, so that's what we saw in that analysis.